the 3,200-degree steel monster that melted workers and fed the war factories. The heat arrives before the sound. It rolls across the factory floor like a living force, pressing against lungs, skin, bone. Men feel it through layers of thick canvas and leather before they even reach the furnace deck. The air itself has weight here. Every breath tastes of iron dust and scorched oil. Above them towers the furnace, 40 feet of steel shell and refractory brick, blowing faintly from the violence inside. Within its sealed chamber, a white-orange ocean churns at nearly 3,200 degrees Fahrenheit, hot enough to liquefy steel beams, vaporize tools, and erase flesh in seconds. A worker known only as Kowalski climbs the iron stairs. Each step rings hollow under his boots. His gloves are blackened from weeks of shifts. Sweat already streams down his neck, despite the winter night outside the plant walls. Below him, conveyor belts grind endlessly, carrying scrap metal toward the furnace mouth like offerings to a mechanical god. Above him, the tapping port begins to glow brighter, the signal. Inside the furnace, hundreds of tons of molten steel are reaching the exact chemical balance demanded by wartime production. Tanks, artillery shells, armor plating, rail lines, the war factories across the nation are waiting for this metal. The foreman shouts a command lost beneath the roar. Valves turn, steel gates shift, the tapping channel opens, then the furnace exhales. A river of molten metal bursts forward white, violent, blinding, spilling into the massive ladle below. The heat spike slams into the workers like a shock wave. Paint blisters from nearby machinery. Leather gloves begin to smoke. Kowalski leans forward to guide the flow. For a moment, everything is perfectly controlled. Then the furnace wall cracks. Not loudly, not dramatically. Just a thin fracture forming deep inside the refractory lining, where temperatures no human structure was ever meant to endure have been building for months. The men cannot see it, but the steel monster already knows. And when it fails, the furnace will not simply break, it will spill the sun onto the factory floor. Steel built the modern world, yet the act of creating it demanded conditions that bordered on the impossible. Inside the great furnace halls of early 20th century steelworks, temperature soared beyond anything the human body was designed to endure. Workers stepped daily into environments where radiant heat could blister skin from several feet away, where iron dust filled the air like metallic fog, and where machinery moved with the indifferent force of geology. Yet the paradox at the heart of industrial steelmaking was not simply heat, it was necessity. Nations required steel in quantities the world had never before imagined. Railways demanded miles of track stretching across continents. Cities demanded beams capable of lifting towers into the sky, and when war arrived, steel became the skeleton of entire armies' armor plate, artillery tubes, ship hulls, aircraft frames, shell casings. Every weapon, every locomotive, every bridge began the same way, as scrap metal and raw iron lowered into furnaces that burned hotter than volcanic lava. To achieve these temperatures, steelmakers constructed enormous open-hearth furnaces capable of sustaining heat above 3,000 degrees Fahrenheit for hours at a time. Inside those chambers, iron and carbon were melted, refined, and transformed into the material that would define the industrial age. But such heat came at a price. The furnaces themselves lived on the edge of destruction. Their inner walls, lined with specialized refractory brick, slowly degraded with every firing cycle. Each batch of molten steel eroded the furnace lining a little further. Every hour of operation pushed the structure closer to collapse. Yet shutting the furnace down was rarely an option. A single furnace could produce hundreds of tons of steel per day. An entire factory depended on its constant operation. Wartime economies especially demanded uninterrupted production. When steel shipments slowed, shipyards stalled, tank assembly lines froze, and entire supply chains faltered. So the furnaces kept running, day after day, week after week, month after month. Workers learned to read the signs of danger the way sailors read approaching storms. A change in the color of the flame, a vibration in the furnace shell, a crack spreading through the refractory lining like a fracture in bone. These warnings mattered because the furnace was not merely a machine, it was a controlled catastrophe. Within its walls existed a lake of molten steel, hotter than the surface of many volcanoes. If containment failed, that liquid metal would escape with unstoppable force flowing across the floor, igniting wood, melting steel equipment, and turning the factory itself into a burning channel of metal and fire. For the men who worked there, the furnace represented both livelihood and threat. It fed their families, it built their nation, and every shift they spent beside it was a quiet wager against physics itself. Steel gave the modern world its strength, but to create it, thousands of workers had to stand within arm's reach of something humanity had only barely learned how to control. When war arrives, steel becomes as essential as soldiers. Factories that once produced rails, bridges, and commercial machinery suddenly face a different mandate. Every furnace must feed a war economy whose appetite grows by the hour. Governments measure victory not only in battlefield gains, but in tons of steel produced per day. In the first half of the 20th century, this demand surged with terrifying speed. A single battleship required over 40,000 tons of steel. Tanks consumed thousands more. Artillery shells, armor plating, aircraft engines, and rail lines for military logistics required vast quantities of precisely refined metal. Entire nations reorganized their industries around one central objective: keep the furnaces burning. Steel plants that once worked moderate civilian schedules transformed into relentless engines of wartime production. 24 hours a day, 7 days a week. The open hearth furnaces, already the giants of industrial metallurgy, became the beating heart of this effort. Each furnace was capable of producing 200 to 350 tons of steel per heat, and many facilities operated multiple furnaces simultaneously. Their combined output fed the shipyards along the coasts, the tank factories inland, and the rail networks carrying weapons toward distant fronts. But this pace came with brutal consequences. Open hearth steelmaking was not a quick process. A single heat could last 8 to 12 hours, during which temperatures remained near 3,200 degrees Fahrenheit. The furnaces had to maintain precise chemical balances to remove impurities like sulfur and phosphorus while controlling carbon content to exact specifications demanded by military engineers. Every batch required constant monitoring. Every adjustment required human hands. Workers stood on furnace decks where the heat radiating from open ports could reach 1,200 degrees Fahrenheit in the surrounding air. Their job was to inspect molten metal samples, regulate fuel flow, and open the furnace to release the glowing steel into massive ladles for transport. Mistakes were unforgiving. Too much carbon and the steel became brittle. Too little and it lost its strength. An improperly timed tap could destroy the furnace lining or flood the factory floor with liquid metal. Under normal conditions, furnaces were shut down periodically for maintenance. Refractory brick linings were replaced. Cracks were repaired. Heat damage was carefully inspected. But wartime pressure changed these rhythms. Maintenance schedules shortened. Shutdowns were postponed. Furnaces that should have rested were pushed into continuous operation. Production quotas climbed higher with each passing month. Government contracts demanded record output. Foremen urged crews to keep the steel flowing regardless of the strain placed on machinery or men. For many workers, the furnace floor became a world without seasons. They entered the mill in darkness and emerged into darkness again, their bodies coated in metallic dust and sweat hardened by the heat. Some labored 12-hour shifts beside open tapping ports where molten steel poured like rivers of light. Accidents increased. Burns were common. Heat exhaustion stalked the furnace decks. Occasionally, the molten steel itself escaped containment, spilling into channels or across the floor in blinding cascades. Yet the furnaces continued, because behind every batch of steel waited a war machine that could not stop. Factories hundreds of miles away depended on those glowing ladles arriving by rail. Shipyards needed armor plate. Tank plants required hardened steel components. Ammunition factories consumed endless supplies of metal for artillery shells. To slow production was to slow the war effort itself. So the furnaces burned hotter, and the men who worked beside them lived closer and closer to the edge of catastrophe. The great steel furnaces of the industrial age did not emerge suddenly. They evolved slowly from centuries of experimentation with fire, iron, and the stubborn chemistry of carbon. Early blast furnaces could produce molten pig iron, but transforming that crude metal into reliable structural steel remained one of the great technical challenges of the 19th century. Steel had to be precise. Too brittle and bridges collapsed. Too soft and armor plate shattered under impact. For decades, metallurgists searched for a method that could produce steel not just quickly but predictably. The first breakthrough came in the 1850s with the Bessemer converter, a towering vessel that blasted air through molten iron to burn away impurities. The process was revolutionary. It could produce steel in minutes rather than hours. But the Bessemer method had limits. It struggled to control phosphorus content and offered little flexibility in adjusting the final chemistry of the metal. Engineers needed something more controlled, something slower but more precise. That solution arrived with the open hearth furnace. Developed in the 1860s by German engineer Carl Wilhelm Siemens and refined by French metallurgist Pierre-Émile Martin, the open hearth process transformed steelmaking into a carefully managed chemical operation. Instead of violent air blasts, the furnace used a regenerative heating system that recycled waste heat from exhaust gases. Flames passed through chambers filled with brick structures that absorbed heat, storing it and releasing it back into the furnace during the next cycle. This ingenious design allowed temperatures to climb beyond 3,000 degrees Fahrenheit, hot enough to melt scrap steel and pig iron together inside a massive shallow hearth. The furnace itself resembled a gigantic brick-lined chamber beneath a curved steel shell. Its interior floor held a wide bath of molten metal, often stretching 20 to 30 feet across. Workers could open inspection ports to observe the metal's glow, take samples, and adjust chemical composition throughout the process. Unlike earlier methods, the open hearth furnace gave metallurgists time. A single heat could last 10 hours or more, allowing operators to gradually refine the molten mixture. Carbon levels could be reduced carefully, alloying elements like manganese could be added in controlled quantities. The resulting steel achieved a consistency earlier generations could only dream of. By the early 20th century, open hearth furnaces had grown into industrial giants. Some weighed hundreds of tons and could hold over 300 tons of molten metal in a single heat. Steel plants built entire furnace halls to house rows of these machines, their arched shells glowing faintly as they worked around the clock. Each furnace became a steel-making ecosystem. Massive charging machines rolled along tracks, dumping tons of scrap metal and iron ore into the furnace mouth. Gas burners roared overhead, feeding flames that rippled across the metal bath like a horizontal storm. Exhaust systems carried waste gases through regenerative chambers that recycled the heat again and again. The process was efficient, relentless, and enormous. From these furnaces flowed the structural steel that reshaped the modern world. Skyscrapers rising in New York and Chicago depended on open hearth steel beams. Railroad empires stretching across continents relied on its rails. Warships, artillery, armored vehicles all demanded steel refined within those blowing chambers. By the 1930s and 1940s, the open hearth furnace had become the dominant steel-making technology across much of the industrial world. Factories built them larger each decade, hotter, more powerful. Each new generation pushed the limits of temperature, scale, and output. But as the furnaces grew larger, the danger inside them grew as well, because controlling 3,200 degrees of molten metal was never a stable achievement. It was a fragile equilibrium, one dependent on brick linings, precise engineering, and human vigilance. And when any of those elements failed, the steel monster revealed what it truly was: a volcano built inside a factory. At a distance, the open hearth furnace appeared almost motionless, a long steel shell, a row of heavy doors, thick pipes feeding fuel and air. To an untrained observer, it resembled a quiet industrial structure resting in the middle of a cavernous building. But inside that shell lived one of the most violent environments ever engineered. The furnace was built in layers, each designed to survive a different assault from heat, pressure, and chemical corrosion. At its core was the hearth, a shallow basin lined with refractory brick capable of withstanding temperatures that could melt ordinary stone. These bricks were not simple construction materials. They were carefully formulated ceramics made from magnesite, silica, and alumina, materials chosen for their ability to endure repeated exposure to temperatures exceeding 3,200 degrees Fahrenheit. Even these specialized materials slowly degraded. Each heat cycle chipped away at the furnace interior. Each batch of molten steel carried microscopic fragments of brick away with it. Above the hearth rose the furnace roof, a curved arch of refractory brick designed to reflect heat downward toward the metal bath. Flames swept across this roof continuously, forming a horizontal storm of fire that maintained the furnace's extreme temperature. Fuel entered through massive burner ports. Early furnaces burned coal gas or producer gas generated from coke ovens nearby. Later installations used oil or natural gas, which allowed operators greater control over flame intensity. The fuel mixed with preheated air inside the furnace, igniting in a roaring stream that raced across the chamber. But the true secret of the open hearth furnace lay beneath it. Below the furnace floor sat two enormous chambers filled with intricate stacks of fire brick known as regenerators. These chambers captured heat from the furnace exhaust gases as they exited the system. The hot exhaust flowed downward through one chamber, heating the brick stacks until they glowed red. After a set interval, often 20 minutes, the airflow direction reversed. Fresh air and fuel gas now passed through the heated chamber before entering the furnace, absorbing the stored heat and raising the flame temperature dramatically. This regenerative cycle allowed the furnace to recycle its own heat again and again. Without it, reaching temperatures above 3,000 degrees would have required impossible fuel consumption. With it, steelmakers could sustain the inferno for hours at a time. Feeding the furnace required machines almost as massive as the furnace itself. Charging machines rolled along tracks in front of the furnace doors, carrying enormous boxes filled with scrap steel, iron ore, and flux materials such as limestone. When positioned correctly, a mechanical arm pushed the charge through the open furnace door, dumping tons of raw material into the glowing chamber. Inside, the metal began to melt almost immediately. Scrap collapsed into the molten bath. Impurities separated into slag, a lighter molten layer that floated on the surface of the steel. Workers monitored this process constantly, extracting small samples of molten metal with long-handled spoons. The samples cooled quickly into solid discs. These discs were then broken open so metallurgists could inspect their internal grain structure and measure chemical composition. Adjustments were made by adding specific alloying elements directly into the furnace. When the chemistry reached the precise balance required, the furnace prepared for its most dramatic moment, tapping. At the base of the furnace wall sat a sealed opening known as the tap hole. Behind it waited hundreds of tons of molten steel. When workers drilled through the clay plug sealing this hole, gravity took control. The steel erupted outward, a blinding white river pouring into a giant ladle lined with refractory brick, capable of holding the molten metal as it traveled to casting stations. In a matter of minutes, the furnace emptied, but the furnace itself remained, still glowing, still burning, still waiting to swallow the next mountain of scrap metal. And as long as the fires stayed lit, the structure endured relentless punishment. Every hour of operation expanded and contracted the furnace shell. Every cycle cracked brick and strained steel supports. Every tap carried away fragments of the furnace's own interior. It was an engineering system designed to contain an artificial volcano. But like every volcano, containment depended on delicate balance. and inside the furnace walls, that balance was always slowly breaking. To the workers on the furnace deck, the flames appeared chaotic. They roared across the chamber ceiling in long orange sheets, twisting and folding like a storm contained within brick walls. Sparks burst from the furnace mouth when the doors opened. Heat waves shimmered through the air, distorting everything beyond the glow. But the violence inside the furnace was not random. It was precisely controlled. Every second of the process depended on maintaining a fragile balance between fuel, air, chemistry, and time. Too little heat and the metal would refuse to melt properly. Too much heat and the furnace lining would begin to collapse. Engineers designed an entire system of controls to maintain that balance. Fuel flow regulators governed the gas feeding the burners. Massive valves adjusted the ratio of air to fuel, determining the intensity and color of the flame. Furnace operators studied these colors constantly because the flame itself revealed critical information about the chemistry inside. A deep yellow flame suggested incomplete combustion. A brighter, sharper flame meant the mixture was correct. Subtle changes in flame length could signal rising carbon levels in the molten metal. In many steel plants, the men running the furnaces relied less on instruments and more on experience. They had spent years watching fire move across the hearth. They could sense when something was wrong by the tone of the furnace roar or the speed at which slag formed on the surface of the metal bath. These operators were known simply as melters. Their authority inside the furnace hall was absolute. A melter decided when to adjust the burners, when to add alloying metals, and when the steel had reached the exact composition required. During wartime production, that judgment carried enormous consequences. If the steel failed quality tests, entire shipments of armor plate or artillery components could be rejected. The melter's eyes, ears, and instincts guided hundreds of tons of molten metal through its transformation, but even the best operator depended on a network of mechanical systems working in perfect synchronization. The regenerative chambers beneath the furnace required constant switching to maintain peak heat efficiency. Large reversing valves controlled this cycle, redirecting airflow every 20 minutes or so. If these valves failed, temperatures inside the furnace could drop rapidly or spike dangerously high. Cooling systems were equally important. Water lines ran along portions of the furnace structure to prevent the outer steel shell from overheating. The shell itself expanded and contracted during each heating cycle, creating tremendous mechanical stress. Engineers installed expansion joints and flexible supports to absorb these movements. Without them, the furnace could literally tear itself apart. Sensors, primitive by modern standards, monitored pressure levels and gas flows. Technicians walked the furnace hall checking gauges, listening for unusual vibrations, inspecting brickwork for signs of cracking, because the furnace was never truly at rest. Even during normal operation, it was fighting against the limits of materials science. Refractory brick slowly weakened under repeated thermal shock. Steel supports warped after months of exposure to radiant heat. Small fissures developed in the lining where molten metal constantly attacked the surface. These defects did not appear suddenly. They grew gradually. At first, they were microscopic fractures hidden deep within the brick lining. Then they widened under pressure and temperature until they formed visible cracks that workers could detect during inspections. A furnace could survive many of these imperfections. But every crack represented a potential path for molten steel to escape, and molten steel did not behave like ordinary liquid. At 3,200 degrees Fahrenheit, it carried the destructive power of a flowing furnace core. If it found even the smallest opening in the lining, it could burn through brick, melt structural steel, and carve its own channel outward. For this reason, furnace crews lived in constant tension between productivity and caution. Shutting the furnace down for repairs could take days. Keeping it running meant trusting that the structure would hold for one more heat, one more tap, one more shift. The engineers who designed these systems understood the danger. They knew the furnace was not merely a machine, it was a sustained reaction between heat and material, a battle between industrial ambition and the physical limits of stone and steel. As long as every component performed its role perfectly, the furnace remained under control. But if even one element failed, the inferno would no longer stay inside its walls. Every furnace carried within it a silent countdown. From the moment the first charge of metal melted inside the hearth, the structure began to deteriorate. No matter how advanced the design or how careful the operators, the extreme conditions inside an open hearth furnace guaranteed that its internal lining would slowly fail. The weakness lay in the refractory brick. These bricks were the only barrier between hundreds of tons of molten steel and the steel framework supporting the furnace. They endured constant exposure to temperatures exceeding 3,200 degrees Fahrenheit, chemical attack from molten slag, and violent thermal expansion as the furnace heated and cooled. Even the strongest refractory materials could not resist these forces indefinitely. Each heat cycle expanded the brick lining as temperatures climbed. When the furnace cooled slightly during tapping and recharging, the bricks contracted again. This expansion and contraction created microscopic fractures deep inside the material. Over time, those fractures spread. The molten steel inside the hearth accelerated the damage. The liquid metal carried dissolved oxygen and carbon that reacted with the brick lining, gradually eating away at its structure. Slag, an aggressive mixture of molten impurities, proved even more destructive. Slag flowed across the furnace floor like a corrosive tide. Where it touched the lining, it stripped away protective layers of ceramic material. The result was a gradual thinning of the furnace walls. At first, the loss was invisible. Only careful measurements during maintenance shutdowns revealed how much refractory brick had eroded. Engineers tracked the depth of the lining using specialized probes, calculating how many heats the furnace could safely endure before repairs were required. But wartime production rarely allowed ideal schedules. Furnaces that should have been shut down after a set number of heats were often pushed further. The demands of steel output outweighed the caution of maintenance planners. As long as the furnace continued producing metal, management hesitated to halt production. Inside the furnace walls, however, the damage continued. Cracks widened under repeated thermal stress. Small cavities formed where molten slag had eaten into the brick. Occasionally, molten steel would seep into these fractures, cooling and solidifying inside the lining like metal veins trapped within stone. This process weakened the structure further. Because solidified steel expanded when reheated, the next furnace cycle could force those cracks even wider. Eventually, the lining reached a critical stage. At certain points along the furnace wall, especially near the tap hole or along the hearth floor, the refractory barrier became dangerously thin. In these locations, only a few inches of ceramic material separated the molten steel bath from the furnace shell. Workers sometimes noticed warning signs, a faint orange glow appearing on the outside of the furnace wall, small sparks where molten metal touched weakened brick, unusual vibrations during tapping operations. These signals meant the furnace lining was approaching failure. If molten steel burned through completely, the result was known as a breakout. A breakout occurred when the molten metal escaped the furnace structure, pouring directly onto the factory floor. Unlike the controlled flow during tapping, a breakout was chaotic and unstoppable. The steel erupted through the wall like a volcanic breach, carrying temperatures capable of igniting nearby equipment and melting structural supports. The danger extended beyond the immediate heat. Molten steel contacting water lines could trigger violent steam explosions. Burning metal could spread through cable trenches, fuel lines, and machinery pits. Entire sections of the plant could be engulfed in fire within minutes. For this reason, furnace crews constantly inspected the structure during operation. But inspections could only reveal what was visible. Deep inside the furnace lining, cracks and voids continued to grow unseen. The men working beside the furnace trusted that the brick would hold. They trusted the engineers who had calculated its limits. They trusted the decades of experience behind the machine. Yet every shift beside the furnace carried the same silent uncertainty. Because somewhere within those glowing walls, the barrier between control and catastrophe was slowly wearing away. And when it finally disappeared, there would be no time to stop what followed. The furnace hall never truly cooled. Even in the depths of winter, when snow gathered along the factory rail lines outside, the interior of the steel mill pulsed with relentless heat. Standing near the furnace deck felt like approaching the open door of a blast furnace, an invisible wall of radiant energy pressing against skin and lungs. Workers called it the heat zone. Inside this zone, temperatures often reached 120 to 140 degrees Fahrenheit in the surrounding air. Closer to the open furnace ports, the heat was far worse. When operators opened inspection doors to observe the molten bath, waves of radiant heat blasted outward, strong enough to ignite grease and blister exposed skin. The men working there wore heavy protective gear, thick leather gloves, canvas jackets treated with fire-resistant oils, steel-toed boots with layers of insulation. But even these protections had limits. Sweat soaked their clothing within minutes. Leather stiffened from repeated exposure to heat. Metal tools grew hot enough to burn through gloves if held too long. A typical shift on the furnace floor lasted 8 to 12 hours. During that time, crews rotated through a series of demanding tasks. Charging operators maneuvered massive machines that pushed scrap metal into the furnace. Slag men skimmed molten impurities from the metal bath using long steel rods. Sample takers leaned dangerously close to furnace openings, dipping metal sponge into the glowing liquid to extract test samples. Every task required precise timing. The furnace did not pause for human fatigue. Communication on the furnace deck relied on shouted commands and hand signals. The constant roar of burners, the grinding of charging machines, and the rumble of overhead cranes made ordinary conversation impossible. Foremen developed simple gestures to coordinate movements across the deck. A raised fist meant stop. Two fingers pointed downward signaled the opening of the tap hole. A sweeping motion warned of approaching ladles. Those ladles were among the most intimidating sights in the mill. Each one was a massive steel vessel lined with refractory brick, capable of holding 200 tons of molten metal. Suspended from overhead cranes, they moved slowly across the furnace hall, glowing faintly from the heat of the steel inside. As they passed, the air around them shimmered like desert heat. A single spill could transform the factory floor into a burning channel of molten metal. Despite the danger, the workers developed a rhythm. Crews memorized the sounds of the furnace the way sailors memorized the sounds of the sea. The roar of the burners, the hiss of gas valves, the scrape of charging machines, each noise carried meaning. A sudden change in tone could signal a blockage, a pressure shift, or the early signs of furnace trouble. Experience became the most valuable tool on the deck. Veteran workers could judge the temperature of the furnace by the color of its glow. They could sense when slag chemistry was changing or when the steel bath was nearing readiness for tapping. Younger workers learned by watching them closely, absorbing knowledge that rarely appeared in written manuals. But experience did not eliminate the risk. Heat exhaustion was constant. Some workers collapsed during long shifts overcome by dehydration and fatigue. Burns were common, sometimes minor, sometimes catastrophic. Occasionally, sparks from the furnace would land on clothing and ignite small fires that workers had to smother quickly. The most feared moment of every shift came during tapping. When the tap hole opened and molten steel surged into the waiting ladle, the furnace released an enormous burst of radiant heat. Workers stood just a few feet away, guiding the flow with long steel tools, ensuring the stream entered the ladle correctly. One slip, one unexpected surge, and the molten metal could spill onto the deck. Despite these dangers, thousands of men returned to the furnace floor every day. Some had grown up in steel towns where furnace work passed from father to son. Others were migrants drawn by wartime wages and the promise of steady employment. Many understood the risks but accepted them as part of industrial life. The furnace paid well compared to many other factory jobs. But the pay came with a cost. Every shift inside the heat zone meant standing within arm's reach of a machine capable of melting steel and everything else around it. And the longer the furnace ran without rest, the more fragile its control became. Failures rarely announced themselves with drama. Inside the steel mill, The shift began like countless others before it. The furnace had already completed several heats during the week, and the refractory lining had endured months of constant exposure to temperatures exceeding 3,000 degrees Fahrenheit. Yet to the workers on the deck, nothing seemed unusual. The burners roared with their familiar thunder, charging machines rolled along their tracks, overhead cranes moved slowly through the haze, carrying empty ladles toward the tapping station. Inside the furnace, nearly 250 tons of molten steel glowed white-hot beneath the roof of brick and flame. The melter studied the furnace through the inspection port. The color looked correct. The slag layer floated evenly across the surface of the metal bath. Chemistry samples suggested the steel had reached the required composition for military production. Tanks and artillery shells waited for this batch. The order was given. Prepare for tapping. Workers moved into position along the furnace deck. The clay seal covering the tap hole was drilled carefully. A faint orange glow appeared as the drill broke through the last thin barrier. Then the steel erupted. A blinding stream burst from the furnace wall, pouring downward into the waiting ladle below. The molten metal flowed with terrifying brightness, lighting the furnace hall like sudden daylight. For several moments, everything proceeded normally. The stream entered the ladle cleanly. Workers guided the flow using long steel bars. Heat waves pulsed outward from the tapping channel. Then something changed. A worker standing near the furnace wall noticed a strange glow beneath the tapping port. At first it appeared as a thin line of orange light running along the outer shell of the furnace, no wider than a finger, but it was not supposed to be there. The glow grew brighter. Inside the furnace lining, molten steel had found a crack that inspectors had never seen. The refractory brick had thinned to only a fragile barrier. Under the pressure of the molten bath, the metal began forcing its way through the weakened wall. Seconds passed. Then the wall failed. A sudden jet of molten steel blasted through the furnace side like a cutting torch. The stream struck the factory floor and exploded into a spray of burning metal droplets. Workers shouted warnings as the breakout widened. More steel followed. Within moments, a second river of molten metal poured from the furnace wall, spreading across the concrete deck in a glowing flood. The temperature of the metal, nearly 3,200 degrees Fahrenheit, instantly ignited wooden equipment, cables, and oil residue on the floor. Panic erupted across the furnace hall. Workers scrambled to escape the advancing flow. Some attempted to redirect the metal using heavy steel plates, but the torrent was unstoppable. Molten steel carved its own channels through machinery and along drainage pits built into the floor. Then the steel reached a water line. When molten metal contacts water, the result can be catastrophic. The water flashed instantly into steam, expanding with explosive force. A violent blast shook the furnace hall, sending fragments of metal and brick across the deck. The pressure wave knocked workers off their feet. The breakout widened further. The furnace wall continued to crumble as molten steel burned through the remaining brick. Hundreds of tons of metal now escaped the furnace simultaneously, some pouring through the tap hole, some flooding from the rupture in the wall. The entire structure began to glow. Superheated steel spread through the lower sections of the furnace platform, melting support beams and igniting nearby machinery. Overhead cranes halted mid-track as operators fled their control cabins. For several terrifying minutes, the furnace hall became a scene of industrial catastrophe. The inferno could not be stopped. The only option was evacuation. Workers ran through corridors illuminated by the reflection of molten metal. Some stumbled through clouds of steam rising from burning pipes. Others helped injured co-workers escape the spreading heat. Behind them, the furnace continued to empty itself onto the factory floor. The steel monster had broken containment, and once released, the sun inside the furnace consumed everything in its path. When the furnace finally emptied, the noise stopped. The roaring burners died as fuel lines were shut down. Overhead cranes hung motionless in the smoky air. The steel mill, normally a place of relentless motion, fell into an uneasy silence broken only by the hiss of cooling metal. Across the furnace floor lay the remains of the breakout. Hundreds of tons of steel had spilled across the concrete deck before finally solidifying into massive twisted slabs. Some sections had cooled into jagged ridges where the metal flowed around machinery and structural columns. Other areas formed thick pools several feet deep, still glowing faintly as heat escaped into the air. The damage was immense. Steel support beams had warped from exposure to the molten flood. Electrical systems had burned out completely. Sections of the furnace platform collapsed where the heat weakened their foundations. Equipment that had taken years to build was now frozen inside a hardened landscape of steel. But the greatest cost was human. Workers who had been closest to the rupture had little time to escape. Some suffered severe burns from the spray of molten metal. Others were injured during the explosion triggered by the waterline. Emergency crews moved cautiously through the furnace hall, searching for the wounded while the metal continued to cool. Rescue operations lasted for hours. Medical teams treated burns, fractures, and heat exposure. Some victims were carried from the mill on improvised stretchers. Others walked out under their own power, their clothing scorched and faces blackened by smoke. Outside the plant, word of the accident spread quickly. Steel towns were tightly knit communities where entire neighborhoods depended on the mill. Families gathered near factory gates waiting for news. Ambulances arrived in steady intervals. The glow from the furnace hall could still be seen against the night sky. Inside the mill, engineers began their grim assessment. The breakout had destroyed the furnace lining completely. Large sections of refractory brick were gone, replaced by frozen steel that had cut through the hearth floor. The outer shell of the furnace had warped beyond repair. Rebuilding would take months. Production would halt. In wartime, that interruption carried serious consequences. Government officials demanded immediate reports explaining the cause of the failure. Investigators interviewed workers, examined maintenance records, and studied the remains of the furnace lining. Their conclusion was familiar. Excessive wear, prolonged operation beyond recommended maintenance intervals. A hidden fracture in the refractory brick that had finally given way under the pressure of molten steel. None of these explanations comforted the families affected by the disaster. For them, the furnace had always been both provider and threat. It offered wages, stability, and purpose. But it also carried risks that few other jobs demanded. The accident simply made that reality impossible to ignore. Within weeks, crews began dismantling the damaged structure. Cutting torches sliced through warped steel beams. Massive cranes lifted away chunks of solidified metal that once flowed like liquid fire. Gradually, the furnace hall returned to order. But the silence lingered. Workers who returned to the deck after the rebuild understood something more clearly than before. The furnace was never fully under human control. It could be managed, contained, disciplined through engineering and experience. But the inferno inside those walls always waited for the smallest weakness, and when that weakness appeared, the steel monster revealed what it had always been. A force only temporarily restrained by brick and steel. The age of the open hearth furnace did not end suddenly. For decades after disasters like the breakout, steel mills around the world continued to operate the same towering machines. Their glowing chambers still melted mountains of scrap and iron, still poured rivers of steel that shaped cities, weapons, and industries. But the lessons of those failures accumulated. Engineers began developing safer and faster methods of steelmaking. By the mid-20th century, new technologies such as the basic oxygen furnace and later electric arc furnaces began replacing the massive open hearth systems. These newer processes produced steel in a fraction of the time and with greater control over chemical composition. Gradually, the steel monsters were retired. Furnace halls that once roared with flame fell silent as their brick chambers cooled for the final time. Some were dismantled for scrap. Others were preserved as relics of an industrial era when humanity first learned to command temperatures capable of melting stone and metal alike. Yet their legacy remains everywhere. In the steel skeletons of bridges, in the armored hulls of ships, in the railways, skyscrapers, and machines that defined the 20th century. Those achievements were forged inside furnaces that burned hotter than any natural fire most people would ever witness. And beside those furnaces stood workers who endured the heat, the danger, and the constant risk that the inferno might escape. The world built from their steel still stands. But the memory of the furnace reminds us that every industrial triumph carries a hidden cost paid in heat, labor, and the fragile boundary between control and catastrophe.